Welcome to the Deep Sleep Science channel. Tonight we drift into the silent, invisible architecture of our cosmos to explore a mystery that holds the stars in their places. As you settle into your blankets and find a comfortable position, imagine the vast velvet darkness of space. Beyond the twinkling lights of distant suns and the familiar glow of our moon, there exists a ghostly substance that we cannot see, touch, or feel, yet it is the very foundation of everything we know. Before we begin our quiet journey into the deep sea of dark matter, please take a moment to gently tap the like button or subscribe to our channel. Your support helps us keep this space a peaceful sanctuary for curious minds. Now, let the weight of the day fade away as we descend into the calm, gravitational embrace of the unseen universe. The universe is a grand, silent masterpiece, and at its heart lies an invisible substance that makes up about 27% of everything that exists. This vast amount of mass energy density is far greater than everything we can see, yet it remains hidden from our eyes, acting as a silent partner to the stars and planets we know so well. While we are familiar with the stars, planets, and even our own bodies, all of this normal matter represents only a tiny fraction, about 5% of the universe. This means that the vast majority of the material world is made of something else entirely, a mysterious presence that outnumbers our familiar world by more than 5 to 1. This mysterious substance is completely invisible because it does not emit, absorb, or reflect any light at all. Because it has no interaction with the electromagnetic spectrum, it cannot be seen by human eyes, or even the most advanced telescopes, remaining a ghost-like presence in the darkness of space. Scientists use the term dark to describe this matter because it simply does not interact with the electromagnetic force. In our daily lives, this force is what allows us to see light, feel the heat of the sun, and touch solid objects. But this substance exists outside of those interactions entirely. One of the most remarkable qualities of these particles is their ability to pass directly through solid objects without leaving a single trace. Whether it is a mountain, a building, or the entire planet Earth, these particles sail through the densest materials as if they were passing through empty air. As you rest tonight, you might find it peaceful to know that billions of these invisible particles are likely passing through your body every single second. They move through us without any friction or impact, a constant silent rain from the cosmos that we can never feel or touch. Despite being called dark, this matter is actually more accurately described as being perfectly transparent. It does not block the light from distant stars or cast shadows. Instead, light travels right through it, unaffected by anything other than the subtle pull of gravity. We only know this substance exists because of its gravitational influence on the things we can see, like stars and galaxies. Just as we can see the wind moving the leaves on a tree without seeing the air itself, we see the effects of this mass pulling on the visible structures of the universe. This invisible presence is often described as the gravitational glue of the cosmos, providing the extra strength needed to hold massive galaxies together. Without this internal binding force, the structures of our universe would be far more fragile and loose than they appear to be. If we were to remove this silent mass from the universe, the stars in the outer regions of galaxies would simply fly off into the emptiness of intergalactic space. The gravity from visible stars alone isn't enough to keep them in their beautiful rotating orbits, meaning we owe the shape of our galaxy to this hidden anchor. Most researchers categorize this substance as cold dark matter, a term that describes particles moving much slower than the speed of light. This cold nature is important because it allows the matter to clump together easily under the influence of gravity, forming the seeds of the universe we see today. While cold is the standard, some theories suggest hot dark matter, which would consist of particles moving at near relativistic speeds, If the universe were made of these fast-moving particles, it would be much harder for large structures like galaxies to form, as the particles would be moving too quickly to settle into clumps. There is also a middle ground known as warm dark matter, which suggests particles with intermediate speeds. This theory is often explored because it might help explain certain small-scale patterns in the way stars are distributed within the smallest galaxies. It is widely believed that this substance is non-baryonic, which is a scientific way of saying it isn't made of protons, neutrons, or electrons. It is fundamentally different from the atoms that make up our world, representing an entirely different branch of the tree of physics. In our own local neighborhood near the Sun, the density of this matter is roughly 0.3 GeV per cubic centimeter. This tells us that even in the seemingly empty space around our solar system, there is a consistent, measurable presence of this invisible material. To put that density into perspective, it is roughly equivalent to the mass of one single proton for every 3 cubic centimeters of space. It is a very thin, spread-out mist, but because it exists everywhere, its total weight becomes truly staggering on a cosmic scale. In the grand tally of the universe, this hidden material is far more abundant than all the gas, dust, and brilliant stars we can observe. It is the dominant form of matter in existence, making the bright parts of the sky seem like mere ornaments on a much larger, darker structure. It is thought that this substance was likely created in the very first moments following the Big Bang, at the dawn of time itself. It has been a part of the universe's story from the very beginning, acting as the foundation for everything that would eventually follow. This matter is the primary reason the early universe was able to form complex structures so quickly after its birth. Because it doesn't interact with light, it was able to start clumping together under gravity long before normal matter could, creating the wells into which gas would later fall to form stars. According to many leading scientific theories, this substance may interact with our world through the weak nuclear force. This is a very subtle interaction that only happens at incredibly short distances, making it extremely difficult to detect, but providing a potential doorway for us to eventually understand its nature. The large-scale structure of our universe is defined by the cosmic web, a vast network of dark matter that acts as a gravitational scaffolding. This web stretches across the entirety of space, providing a framework that dictates where every galaxy and star cluster is allowed to grow. Vast filaments of dark matter stretch across the emptiness, connecting galaxy clusters over distances of billions of light years. These invisible bridges are the largest structures in existence, forming the highways of the cosmos along which matter travels and settles. These long filaments exert a gentle but persistent pull, drawing in nearby gas and dust toward the points where they intersect. It is at these intersections that the density becomes high enough for the first stars to ignite, turning the invisible web into a map of light. If you look at the universe on its largest scale, you will see that galaxies are situated at the nodes or hubs of this massive, invisible web. Much like cities built at the crossroads of major roads, galaxies thrive where the dark matter density is at its highest. Between these dense filaments lie vast regions known as voids, which are largely empty of both dark matter and the normal matter that makes up galaxies. These bubbles of emptiness can be hundreds of millions of light years across, representing the true quiet of the deep universe. In the very early stages of the cosmos, dark matter was the very first substance to begin collapsing into clumps under the force of gravity. Because it was unaffected by the intense radiation of the early universe, it could begin building structures while the rest of the matter was still being pushed around by light. These initial clumps are known as dark matter halos, spherical regions of high density that served as the birthplaces for everything we see. These halos acted as gravitational traps, catching the passing hydrogen gas and holding it still long enough for stars to begin to form. Every large galaxy in existence, including our own Milky Way, is safely embedded inside one of these massive dark matter halos. We are essentially living inside a giant, invisible bubble of mass that extends far beyond the furthest stars we can see in the night sky. The dark matter halo that surrounds the Milky Way is remarkably massive, estimated to be roughly 10 times more heavy than the visible disk of stars. This means that our home is mostly made of the unseen, with our spiral arms being just a small, bright decoration in the center. Powerful computer simulations, such as the Millennium simulation, allow scientists to visualize how dark matter shapes the large-scale structure of the universe. By processing billions of data points over cosmic time, these models show us the slow, graceful dance of invisible particles forming the web of reality. These digital recreations track the movement of billions of individual dark particles across 13 billion years of history. They reveal that the universe we see today is the result of a very specific and patient process of gravitational attraction that started just after the beginning of time. Over the long eons of cosmic history, smaller dark matter halos have merged together to create the massive, complex ones we observe today. This slow accumulation of mass is like small streams joining together to form a mighty river, eventually creating the gravitational power of a galaxy. This specific way of building the universe is known by scientists as hierarchical structure formation. It describes a bottom-up process where the smallest things form first and then gradually combine into larger and larger structures, from dwarf galaxies to massive clusters. Dark matter plays a vital role in protecting galaxies from being ripped apart by the constant expansion of the universe. Within local clusters, the extra gravity provided by this invisible mass keeps the galaxies bound together, allowing them to remain neighbors despite the stretching of space. This mass also influences what is known as the peculiar velocity of galaxies, which is their movement beyond the general expansion of the universe. It is the reason galaxies drift toward one another or swirl in clusters, following the hidden contours of the gravitational landscape. In one particular region of space, there is a massive concentration of dark matter known as the Great Attractor. This area is so heavy and its pull so strong that it is slowly drawing our own galaxy and thousands of others toward it through the darkness. The way dark matter is spread out within a halo usually follows a specific mathematical pattern known as the Navarro-Frank-White, or NFW, profile. This model helps scientists predict exactly how the density of the invisible mass changes as you move from the edge of a galaxy toward its center. According to this profile, dark matter is most concentrated at the very heart of a galaxy, creating a dense spike of gravity at the center. This central concentration helps stabilize the galactic core and supports the movement of the stars that live there. Interestingly, there are some dwarf galaxies in the universe that appear to be made almost entirely of dark matter, with very few stars at all. These rare objects are like ghosts massive enough to pull on their neighbors, but so dim that they are nearly impossible to find. These dark galaxies have enormous gravitational signatures that tell us they are heavy, yet they contain almost no visible light. They are pure examples of the dark matter halos that exist everywhere, reminding us that the universe is full of structures that remain hidden from our view. In the vast theater of space, dark matter acts as the primary director of how galaxies grow and change over billions of years. While stars provide the light, dark matter provides the structural integrity, ensuring that as galaxies spin and move, they remain cohesive units, rather than dissolving into a chaotic mist of lonely stars. One of the most profound roles of this invisible substance is seen in how it dictates the shape and size of the disks in spiral galaxies, like our own Milky Way. The gravity from the dark halo acts like a protective container, pressing inward and allowing gas to settle into a flat, elegant rotating disk where new suns can eventually be born. Within these spiral galaxies, dark matter also performs a stabilizing role by preventing the central bar, a long structure of stars often found in the middle, from growing too large or unstable. By providing a consistent gravitational background, it keeps the core of a galaxy balanced, allowing the spiral arms to maintain their graceful, sweeping curves over eons. Beyond the main body of a galaxy, dark matter is responsible for holding satellite galaxies, such as the Large and Small Magellanic Clouds, in a permanent orbital dance. These smaller clusters of stars are tethered to the Milky Way by the immense pull of our dark halo, preventing them from drifting away into the cold, empty reaches of intergalactic space. Cosmologists have noted a curious puzzle known as the missing satellites problem, which arises when our computer models predict thousands of tiny dwarf galaxies should exist around us. Because we only see a few dozen, it suggests that many of these satellites might be dark, containing vast amounts of dark matter, but almost no stars to light them up. As these satellite galaxies move through the larger dark halo of a parent galaxy, they often leave behind tidal streams of stars. These long, thin ribbons of light are created as the dark matter's gravity gently peels stars away from the smaller galaxy, stretching them out into beautiful, luminous tracks that map the invisible currents of space. Dark matter also assists in the grandest events in the universe, the merging of two massive galaxies. It creates a specialized friction-like effect called dynamical friction, which acts like a thick syrup that slows down moving objects, eventually causing two passing galaxies to spiral into one another, become a single, larger entity. When a smaller galaxy travels through a massive dark halo, it actually creates a wake of dark matter behind it, much like the ripples trailing behind a boat in a still lake. This wake of invisible mass exerts a backward pull on the galaxy, gradually draining its energy and pulling it toward the center of the larger gravitational well. Because of this constant process of attraction, galaxies located in the centers of large clusters are often much larger than average because they have cannibalized their neighbors. This cosmic growth is fueled by the dark matter that acts as a bridge, bringing galaxies together until they eventually merge into giants. Interestingly, the ratio of dark matter to normal matter is not always the same. Everywhere you look, it can vary significantly from one corner of the sky to another. While most galaxies are dominated by the invisible, astronomers have discovered rare cases where the proportions are shifted, revealing a diverse cosmic landscape. One famous example is the galaxy known as NGC 1050 2DF2, which appears to have almost no dark matter at all. For a long time, this was a mystery, but scientists realized that finding a galaxy without dark matter actually proves that it is a real physical substance that can be separated from stars and gas. The density of dark matter in a particular region also has a direct influence on how quickly new stars can form. By pulling gas together into tight, high-pressure clouds, dark matter creates the perfect merceries where gravity can eventually crush hydrogen until it ignites into a brand new star. In addition to building things, dark matter acts as a massive protective shield for galaxies, preventing high-speed cosmic winds from blowing all the life-giving gas out into space. It provides a heavy bucket that keeps the ingredients for future planets and stars safely tucked inside the galaxy's boundaries. Even our own sun's journey through the Milky Way is influenced by this invisible presence, moving in a gentle bobbing motion as it passes through the dark matter disk. This rhythmic rise and fall is a testament to the silent hand of gravity guiding our solar system on its multi-million-year orbit. On an even larger scale, dark matter is the reason why we observe what are called baryon acoustic oscillations, or BOU. These are essentially frozen ripples in the way galaxies are distributed across the sky left over from sound waves that traveled through the hot, dense soup of the very early universe. These ancient ripples provide a ruler for the cosmos, and their specific scale is determined by the amount of dark matter present at the beginning of time. By measuring these ripples, scientists can look back billions of years to see how the invisible was already shaping the visible world. When we look at the total recipe of the universe, we find that matter both visible and dark makes up about 31% of the total density. Since we know that visible atoms are only a small sliver, this number highlights just how much of our reality is built upon this silent, non-reflecting foundation. In the grand evolution of space, dark matter and dark energy are competing forces with very different goals. While dark matter acts as an attractive force that tries to pull things together into clusters, dark energy acts as a repulsive force that tries to push everything apart. For the first 9 billion years after the Big Bang, dark matter was the undisputed champion, dominating the expansion of the universe and allowing structures to grow. During this long era, the pull of gravity was strong enough to slow down the expansion, creating the dense clusters of galaxies we see today. However, about 5 billion years ago, the balance shifted, and dark energy took over as the dominant force in the cosmos. Since that moment, the expansion of the universe has been accelerating, making the gaps between distant galaxy clusters grow wider and wider every second. This specific moment in history, when the strength of matter and the strength of dark energy were roughly equal, is sometimes called the cosmic coincidence. It is a unique window in time that allowed for the formation of large-scale structures just before the universe began its runaway expansion. Dark matter is also essential for a phenomenon known as the integrated Sachs-Wolf effect, which describes how light changes energy as it travels. As a photon of light falls into of dark matter gravity, it gains a tiny bit of energy, and as it climbs back out, it loses it, leaving a signature on the cosmic background. When we look at the light from incredibly distant quasars, we see a series of absorption lines known as the Lyman alpha forest. These lines are caused by the light passing through thin clouds of neutral hydrogen gas that are trapped within the long filaments of the dark matter web. By carefully analyzing this forest of light, scientists are able to create a 3D map of where dark matter was located in the extremely distant early universe. It allows us to see the scaffolding of the cosmos as it looked when the universe was only a fraction of its current age. The total mass of dark matter in the universe is what determines the critical density needed to give space its specific shape. Observations show that our universe is flat, meaning that the amount of dark matter and energy is perfectly balanced to keep parallel lines of light from ever crossing or diverging. If the universe contained significantly more dark matter than it currently does, the force of gravity might have eventually won the tug-of-war against expansion. In that version of reality, the entire universe would eventually stop growing and collapse back in on itself in a violent event called the Big Crunch. With the amount of dark matter we actually have, the universe is expected to continue its journey of expansion forever. We live in a world where there is just enough invisible glue to hold galaxies together, but not enough to stop the rest of space from growing larger and colder. One of the most comforting aspects of dark matter is that it does not appear to evolve, rot, or decay significantly over billions of years. It is a stable, persistent part of the cosmic fabric that remains unchanged even as stars burn out and entire galaxies collide and reshape themselves. The specific ratio of 5 parts dark matter to every 1 part normal matter is considered one of the great fine-tuning mysteries of physics. If this ratio were even slightly different, the universe might have ended up as a dark, empty void without stars, or a dense thicket of black holes. During the first few minutes of the universe, a process called Big Bang nucleosynthesis created the first-like elements like helium and lithium. The presence of dark matter during this time influenced the pressure and temperature of the universe, leaving a fingerprint on the chemical makeup of the stars we see today. Because it is so stable and does not interact with heat or light, dark matter is the most reliable and pure part of the cosmic recipe. It provides a constant, unmoving background that stays steady, while the rest of the visible universe undergoes a constant cycle of birth, death, and transformation. Some theoretical models suggest that in the very early universe, there may have been dark stars that were much larger and cooler than the stars we know. These giants would not have been powered by nuclear fusion, but rather by dark matter particles colliding and destroying each other in their cores. These dark stars would have been truly massive, perhaps thousands of times larger than our Sun, and they would have glowed with a soft infrared light. They would have been the very first lights in the universe, fueled by the invisible energy of the dark matter halos in which they were born. Such stars would have been effectively immortal, as long as there was a steady supply of dark matter to fall into their centers and provide fuel. They represent a fascinating possibility of a different kind of life for matter, one that relies entirely on the unseen world to shine. In the 1970s, Vera Rubin noticed something strange. The stars on the outskirts of galaxies were moving just as fast as the stars near the center. This defied the laws of physics, which suggested that objects further away from a center of mass should move slower, much like the outer planets in our solar system move slower than Earth. This discovery led to the realization that there must be a massive, invisible halo of matter surrounding every galaxy, providing the extra gravity needed to keep those outer stars moving fast. This was the first robust, modern evidence that dark matter wasn't just a theory, but a necessary part of how galaxies work. To help map this hidden mass, the Hubble Space Telescope uses a technique called gravitational lensing to create 3D maps of dark matter clumps. By looking at how the gravity of a cluster of galaxies distorts the light from objects behind it, we can see where the invisible mass is concentrated. The Hubble observations have shown that dark matter is not just a smooth mist, but is concentrated into specific structures and peaks. These maps serve as a visual guide to the unseen, showing us that the empty space between galaxies is actually filled with complex, heavy structures. Over the decades, dark matter research has successfully transitioned from a fringe idea that people doubted into the absolute cornerstone of modern cosmology. Today, it is part of the standard model of the universe, and we simply cannot explain the world around us without acknowledging its presence. Dark matter also plays a role in the phenomenon of gravitational redshift, where light loses energy as it climbs out of a deep gravitational well. By measuring how the color of light shifts as it leaves a galaxy cluster, astronomers can calculate exactly how much dark matter is hiding within that cluster. Advanced scientific techniques like phase space analysis allow researchers to track the individual paths that dark matter particles might take as they swirl around a halo. This mathematical approach helps us understand the wind of dark matter that flows through our own solar system as we move through space. In some regions of a galaxy, dark matter density might become theoretically infinite, creating what are called caustics. These invisible, high-density ridges could act as natural magnifying glasses for space-time, potentially helping us see even deeper into the distant reaches of the universe. Some theories suggest that dark matter particles might actually interact with each other, a concept known as self-interacting dark matter. If this is true, it would mean that dark matter isn't just a ghost, but can bump into itself, which would explain why some galaxy cores look smoother and more spread out than others. The core cusp problem is a famous debate among scientists. where computer models predict a very sharp, dense point of dark matter at a galaxy's center, but our observations often show a flatter core. This suggests there are still subtle details about dark matter's behavior that we are waiting to discover. One possible solution to this problem is that the energy released from exploding stars, or supernova, might be strong enough to push some of the dark matter away from the center. This stirring of the cosmic pot shows how the visible and invisible worlds can influence each other in unexpected ways. When a small galaxy gets too close to a large one, it undergoes tidal stripping, where the larger galaxy's gravity peels away the smaller one's outer layers. Interestingly, the dark matter is often the first thing to be stripped away, leaving behind a naked galaxy that is far lighter than it used to be. By observing these stripped galaxies, scientists can track the path that a galaxy has taken as it fell into a cluster, much like following footprints in the snow. The way the dark matter is distributed reveals the history of the galaxy's long journey through the gravitational landscape. Some models of the universe suggest that dark matter could be warm enough to move at speeds that prevent it from clumping into very tiny structures. If this is the case, it would explain why we don't see as many tiny mini-galaxies as we might otherwise expect to find in the deep sky. There is also a curious and unexplained link between the amount of visible matter and the amount of dark matter in a galaxy, known as the radial acceleration relation. This puzzle suggests that the two types of matter are always perfectly in sync, even though they are made of completely different things. As we move forward into the future, we are building even more sensitive tools like the Einstein telescope to look for the subtle ripples in space-time that dark matter might leave behind. These future discoveries will continue to reveal the quiet, constant presence that has guided the stars since the beginning of time. By going nearly a mile underground, researchers can escape the constant noise of cosmic rays that rain down from space and interfere with delicate instruments. In these deep, quiet caverns, like the one housing the LUX Zeppelin experiment in South Dakota, the Earth itself acts as a massive shield, allowing only the most ghostly particles to pass through. The LUX Zeppelin experiment uses a massive, specialized tank filled with several tons of liquid xenon, a rare and heavy gas that has been cooled until it becomes a clear, dense fluid. Xenon is chosen because its large, heavy atoms provide a big target for a passing dark matter particle to potentially bump into. When a dark matter particle finally strikes the center of a xenon atom, it causes a tiny, microscopic flash of light, known as a scintillation. This flash is so faint and brief that it would be completely invisible to the human eye, representing the moment two different worlds briefly touch. To see these tiny sparks, the tank is surrounded by incredibly sensitive sensors called photomultiplier tubes, which act like high-powered electronic eyes. These sensors are capable of detecting a single photon of light, turning that tiny flash into an electrical signal that scientists can study on their monitors. In Italy, deep beneath a mountain, the Xeno-NNT experiment uses similar liquid xenon technology to listen for the whispers of the universe. By placing the detector inside the Gran Sasso mountain, researchers use thousands of feet of solid rock to block out the chaotic energy of the sun and stars. China also hosts a major search for the unseen at the Jinping Underground Laboratory, which is currently the deepest laboratory in the entire world. The Panda X experiment operates there, taking advantage of the extreme depth to create the most peaceful environment possible for catching a glimpse of a dark matter particle. Another way to find these particles is by using ultra-cold crystals made of silicon and germanium, as seen in the Super CDM's experiment. Instead of looking for a flash of light, this experiment waits for a tiny thump a microscopic vibration of heat created when a particle hits the crystal lattice. To make this work, the detectors must be cooled to temperatures near absolute zero, which is the coldest temperature possible in the universe. At this extreme cold, the atoms in the crystal are almost perfectly still, so even the tiniest nudge from a dark matter particle can be felt as a sudden change in temperature. While some look for heavy particles, the ADMX experiment uses a powerful magnetic field to search for a much lighter candidate called the action. This experiment is designed to act like a very sensitive radio, trying to tune in to the specific frequency where an action might convert into a detectable photon of light. The researchers at ADMX must slowly turn their radio dial, scanning through millions of different frequencies one by one. It is a patient and quiet process as they listen for a very specific hum that would confirm the universe is filled with these wave-like particles. In Italy, a project called Dharma/Libra has reported seeing a strange annual modulation in their data for over 20 years. They noticed that the number of signals they detect rises and falls in a predictable rhythm as the seasons change throughout the year. The theory behind this is that as Earth orbits the Sun, it moves through a dark matter wind created by our solar system's journey through the galaxy. In the summer, we are moving faster into this wind, and in the winter, we are moving slightly slower, which should cause a rhythmic change in detections. Despite these intriguing results, other experiments around the world have not yet been able to find the same pattern in their own data. This has created a friendly but rigorous debate in the scientific community as researchers work to understand if the signal is truly dark matter or something else entirely. The Deep 3600 experiment takes a different approach by using a large sphere of liquid argon instead of xenon to look for interactions. Argon is much easier to find and clean than xenon, and it has a unique way of glowing that helps scientists distinguish a real particle hit from background radiation. In Canada, a repurposed neutrino observatory called SNO+ has also joined the hunt, using its deep underground location to look for rare events. By using a massive acrylic sphere filled with special fluids, it provides another unique ear to listen for the silent movements of the dark universe. To ensure the results are accurate, scientists must use low background materials that are not naturally radioactive, such as lead recovered from ancient Roman shipwrecks. This lead has spent 2,000 years underwater, allowing its natural radioactivity to decay until it is incredibly quiet and stable. This ancient lead is used to build a wall around the detectors, acting as a final barrier against any stray energy from the surrounding rock. It is a beautiful irony that some of the oldest artifacts of human history are being used to help us discover the secrets of the beginning of the universe. The detectors are also often placed inside massive tanks of pure water, which acts as a buffer to catch stray neutrons before they can hit the sensors. Water is excellent at slowing down and absorbing these particles, ensuring that only a true dark matter signal can make it through to the center. So far, after decades of patient waiting, no experiment has conclusively caught a dark matter particle in the act of colliding. However, every day that passes without a detection actually helps us by narrowing the search, telling us exactly what dark matter isn't, so we can get closer to what it truly is. While some look underground, the Fermi Gamma Ray Space Telescope looks high above the atmosphere for gamma rays produced when dark matter particles collide. In the densest parts of space, these particles might occasionally annihilate each other, releasing a burst of high-energy light that we can see from orbit. These collisions are most likely to happen in the very center of our galaxy, where the dark matter is packed together most tightly. By pointing our telescopes at the heart of the Milky Way, we are looking for a subtle, ghostly glow that shouldn't be there according to our maps of normal stars. astronomers have actually noticed an unexplained galactic center excess of gamma rays that seems to fit the pattern of dark matter annihilation. This discovery has caused much excitement, as it could be the first direct evidence of the invisible world's secret energy. However, science is always cautious, and some argue that this excess light could simply be coming from a large, hidden population of rapidly spinning stars called pulsars. The debate continues as we gather more data, peeling back the layers of the galactic core to find the truth. On the International Space Station, the Alpha Magnetic Spectrometer, or AM02, is currently searching for antimatter that might be created by dark matter. This incredibly complex machine filters through millions of cosmic rays every day, looking for rare particles that defy the normal laws of physics. AM02 has detected an unexpected abundance of positrons, which are the antimatter version of electrons, zipping through space. This positron excess is another potential clue, suggesting that something invisible out there is constantly creating new particles and flinging them toward us. To understand the big picture, the Planck satellite measured the cosmic microwave background, the afterglow of the Big Bang, with incredible precision. By looking at the tiny hot and cold spots in this ancient light, scientists can calculate exactly how much dark matter was present when the universe was young. The data from Planck shows us that the universe is remarkably flat and balanced, a state that is largely maintained by the density of dark matter and dark energy. This ancient light acts as a blueprint, confirming that the invisible architecture of the universe has been stable for billions of years. The Euclid mission was recently launched with the specific goal of mapping the geometry of the dark universe. By observing billions of galaxies across more than a third of the sky, it is creating the most detailed map ever made of how dark matter is spread out across space. Euclid uses a technique called weak gravitational lensing, where it looks for the tiny, subtle distortions in the shapes of distant galaxies. These distortions are like the ripples you see at the bottom of a pool, revealing the invisible water of dark matter that is bending the light. The James Webb Space Telescope is also contributing by looking back in time to see the very first galaxies that ever formed. By seeing how these early star systems are arranged, scientists can learn about the seeds of dark matter that first pulled them together in the darkness of the early universe. Webb is also helping us investigate the possibility of dark stars, which might have been the very first objects to shine in the cosmos. If these massive, cool stars existed, they would have been powered by the energy of dark matter, and Webb is the only telescope powerful enough to find their faint signatures. The Gaia Observatory is currently mapping the positions and movements of over 1 billion stars in our own Milky Way with unprecedented accuracy. By watching how these stars move over time, we can weigh our galaxy and calculate the exact mass of the dark halo that surrounds us. We are also learning that dark matter can act as a trap for high-speed cosmic rays, subtly changing the time it takes for them to travel through the galaxy. By studying these arrival times, we can learn more about the density and texture of the invisible mist that fills our galactic neighborhood. When two black holes merge, they send out ripples in space-time called gravitational waves, and these waves can be influenced by dark matter. If a black hole is surrounded by a dark matter spike, it might change the way the black hole spins or moves, leaving a signature in the ripples we detect on Earth. The Vera C. Rubin Observatory is about to begin a massive 10-year survey that will track how dark matter influences the expansion of space over time. This project will take millions of high-resolution images, allowing us to watch the silent evolution of the cosmic web in real time. To avoid interference, some scientists look for dark matter in dwarf spheroidal galaxies, which are small, quiet galaxies that contain very little gas or dust. Because these galaxies are so simple and clean, any strange light or movement we see is much more likely to be caused by dark matter. Researchers also look for spectral line-specific colors of light that might be emitted if dark matter decays or interacts in the X-ray or gamma-ray bands. These lines would be like a fingerprint, identifying the exact mass and energy of the dark matter particle for the very first time. The Chandra X-ray Observatory has been used to map the hot gas trapped in massive galaxy clusters to see how it follows the hidden gravity of dark matter. By comparing the location of the gas to the location of the stars, we can see exactly where the invisible mass is doing its work. Finally, we have even detected dark matter bridges, long, thin threads of invisible mass that stretch between two separate galaxies. These bridges were found by looking at how they subtly bend the light of even more distant objects, proving that the galaxies are connected by a hidden web. The quiet depths of the particle world are filled with subtle interactions that we are only just beginning to name. In the grand tapestry of physics, there is a concept known as collisionless matter, which is exactly how dark matter behaves. Unlike the atoms in a billiard ball that bounce off one another, dark matter particles simply glide right through each other, never clashing or exchanging energy through touch. Which is why the large-scale structures they form remain so calm and ghostly. This lack of interaction means that dark matter does not have a temperature in the way we usually think about it. In our world, temperature comes from atoms jiggling and bumping into each other, sharing heat, but because dark matter doesn't bump, it cannot radiate heat away or cool down like a hot cup of tea, staying in a state of chaos. Perpetual, silent motion. Some physicists explore the idea of milli-charged dark matter, suggesting these particles might carry a tiny, almost infinitesimal amount of electric charge. If this were true, it would mean that dark matter isn't completely cut off from the world of light and magnets, but interacts with it so weakly that it would take billions of years to notice even a small nudge. If dark matter particles ever do collide in a specific way, they might undergo annihilation, where two particles vanish and turn into a pair of familiar particles, like photons of light. This process would be a rare bridge between the dark world and our own, sending out a faint signal of high-energy light that acts as a beacon for our telescopes in the deep black of space. Currently, the standard model of particle physics, our best guidebook for how the universe works, does not actually include a spot for dark matter. This tells us that our understanding of nature is still incomplete, and that there is a whole extra chapter of physics waiting to be written that explains the 85% of matter we cannot yet see. For dark matter to exist today, its particles must be incredibly stable, lasting for billions of years without falling apart. If they were prone to decaying into other things, the gravitational glue holding our galaxy together would have dissolved long ago, and the stars would have drifted away into the dark. In a different theory called self-interacting dark matter, or SIDM, researchers imagined that dark matter particles can actually scatter off each other like soft cotton balls. This gentle scattering would change the shape of galaxy centers, making them more rounded and less peaked than we would expect from particles that never touch. This scattering might be the key to solving the cusp core problem, which is a fancy way of saying that our computer models predict a very sharp point of matter at a galaxy's center, while our telescopes see a flatter, smoother distribution. If the particles can push against each other, they would naturally spread out, creating the softer cores we actually observe. It is even possible that dark matter is just the tip of the iceberg, part of a whole dark sector with its own invisible forces. Imagine a hidden version of nature with its own dark electromagnetism and dark atoms that we can't see, existing right alongside us but completely out of reach of our five senses. Some models suggest that dark matter is asymmetric, much like normal matter is. Just as there is more matter than antimatter in our world, which is why we exist, there might be more dark matter than anti-dark matter, a cosmic imbalance that occurred at the very beginning of time to ensure the universe had enough mass to grow. The mass of these particles could be almost anything, from the incredibly tiny to the unimaginably large. Some theories suggest a particle so light it is called fuzzy dark matter, where each individual particle is so spread out by quantum mechanics that it is as large as an entire galaxy, behaving more like a giant, vibrating wave than a solid speck. This quantum wave-like nature would act as a natural limit on how small a clump of dark matter could be. Because waves don't like to be squeezed into tiny spaces, this fuzziness would prevent the invisible mass from clumping into very small points, explaining why we don't see tiny micro-galaxies scattered throughout the void. Scientists measure the likelihood of particles hitting each other using something called a cross-section. It's like measuring the size of a target for dark matter. This target is so incredibly small that millions of particles can stream through a lead wall without a single one hitting an atom, making the search for them the sun. Ultimate exercise in patience. Our experiments have set extremely low limits on this cross-section, proving that if dark matter does hit things, it happens less often than a single grain of sand hitting a specific bird in a rainstorm. This extreme rarity is why we build detectors the size of houses and hide them deep underground. One intriguing idea is the Higgs portal, which suggests that dark matter might interact with the Higgs boson particle that gives everything mass. If the Higgs is the doorway between our world and the dark one, then by studying how the Higgs behaves in particle accelerators, we might catch a glimpse of the dark world on the other side. Other physicists think dark matter might be a composite particle made of even smaller, hidden components held together by a dark force we haven't discovered yet. Just as protons are made of quarks, dark matter could be a complex structure that only looks like a simple particle from far away. Over long periods of time, dark matter particles might get captured by the gravity of massive objects like our Sun. As they drift through the solar system, they could get pulled into the Sun's core, slowly sinking to the center and accumulating there in a silent, invisible pile over billions of years. If enough of these particles gather in the Sun's center, they could theoretically change how heat is moved from the core to the surface. By acting as a subtle heat conductor, the dark matter could slightly alter the temperature of the Sun, giving us a tiny, measurable clue about its existence right in our own backyard. In the early universe, dark matter was the essential ingredient that allowed the first stars to ignite. Without its extra gravity to pull gas together quickly, the universe would have remained a smooth, boring cloud of hydrogen for much longer, delaying the birth of light by millions of years. The very first stars were born inside what are called mini-halos, which were the smallest seeds of dark matter. These tiny pockets of gravity were only about 1 million times the mass of our Sun, small by cosmic standards. But they were the high-pressure cradles that gave birth to the very first light in the darkness. Dark matter also acts as the ultimate architect for the disks of spiral galaxies, providing the heavy foundation that allows gas to flatten out as it spins. Without this invisible weight, the gas would likely stay in a messy, spherical cloud, and the beautiful spiral arms we see in the night sky would never have formed. Inside those galaxies, dark matter prevents the central bar of stars from growing too large or spinning too fast. By acting like a gravitational brake, it keeps the center of the galaxy stable, ensuring that the heart of the Milky Way remains a balanced and productive place for stars to live. Tiny satellite galaxies, like the Magellanic Clouds that orbit our own, are held in place by the massive pull of our galaxy's dark halo. It acts like an invisible leash, keeping these smaller collections of stars from drifting away into the lonely, cold reaches of intergalactic space. There is a mystery called the missing satellites problem, where our computer models predict that there should be thousands of tiny galaxies around the Milky Way, but we only see a few dozen. This suggests that the universe might be full of dark galaxies, clumps of dark matter that were never able to pull in enough gas to start making stars. Sometimes we can see tidal streams of stars being pulled out of these smaller galaxies by the gravity of the Milky Way's dark halo. These long, glowing ribbons of stars are like cosmic footprints, showing us exactly where the invisible dark matter is pulling most strongly as it slowly dissolves its smaller neighbors. Dark matter also helps galaxies merge together through a process called dynamical friction. As two galaxies pass each other, their dark halos create a kind of gravitational drag, like moving your hand through water, which slows them down and eventually causes them to spiral inward and become one. When a small galaxy moves through a much larger dark halo, it leaves a wake of dark matter behind it, much like the ripples behind a boat. This wake of extra mass pulls back on the moving galaxy, acting as a silent, invisible anchor that slowly drags the galaxy toward the center of the cluster. Because of this constant pulling, galaxies at the center of large clusters often grow to be enormous, cannibalizing their smaller neighbors over billions of years. This growth is only possible because dark matter provides the extra gravity needed to bring these distant islands of stars together. The amount of dark matter compared to normal matter can vary wildly. While most galaxies have about 5 times as much dark matter, some rare ones seem to have almost none. Finding these empty galaxies is actually a great discovery because it proves that dark matter is a real physical substance that can be separated from stars. One such galaxy, NGC 1052DF2, has puzzled astronomers because it appears to be a see-through galaxy with very little invisible mass. It reminds us that the universe is a diverse place and that the relationship between light and shadow is more complex than we once thought. The density of dark matter in a galaxy also controls the speed limit for star formation. By pulling gas into dense, high-pressure pockets, dark matter creates the perfect conditions for new suns to be born, acting as the silent gardener that tends to the growth of the visible universe. It also acts as a protective shield, holding a galaxy's gas in place so that intense cosmic winds don't blow it all away. This gravitational bucket ensures that a galaxy keeps its ingredients for future generations of stars, rather than losing them to the empty void. Even our own sun's path through the Milky Way is a gentle, bobbing motion influenced by the dark matter that sits in the galaxy's disk. As we travel, we rise and fall through this invisible sea, a rhythmic dance that has lasted for billions of years, guided by a force we cannot see. On a cosmic scale, dark matter is the reason why baryon acoustic oscillations exist. These are essentially giant, frozen sound waves from the beginning of time that left a pattern in the way galaxies are spread across the sky today, acting as a map of the invisible world's early history. These ancient ripples are like the rings in a tree trunk, telling us exactly how much dark matter was present in the early universe. By measuring the distance between these ripples, scientists can calculate the expansion of the universe with incredible accuracy. In the grand tally of everything, matter both the kind we can see and the kind we can't makes up about 31% of the universe. This balance is what determines whether the universe will expand forever or eventually fall back together, making dark matter a key player in the ultimate fate of all things. Dark matter and dark energy are like two cosmic rivals. While dark matter uses gravity to pull things together into beautiful structures, dark energy is a mysterious force that pushes space apart, making the universe grow larger and emptier every second. For the first 9 billion years of history, dark matter was winning the tug-of-war, allowing galaxies and clusters to form and thrive. It was an era of building and connection, where gravity was the dominant force shaping the young and growing cosmos. But about 5 billion years ago, the balance shifted, and dark energy took the lead. Since then, the expansion of the universe has been speeding up, and the vast webs of dark matter are slowly being stretched thinner and thinner as the galaxies move further apart. This transition period is often called the cosmic coincidence because we happen to live at a time when the strength of dark matter's pull and dark energy's push are roughly equal. It is a unique moment in the long life of the universe that allows us to see both forces at work. Dark matter is also responsible for the integrated Sachs-Wolf effect, where light from the Big Bang changes energy as it passes through giant clumps of invisible mass. By studying these tiny changes in the light's color, we can map the growth of the largest structures in the universe. When we look at light from distant quasars, we see a Lyman alpha forest, which is a series of shadows cast by hydrogen gas trapped in the dark matter web. This forest allows us to see the invisible threads of the universe stretching back billions of years into the past. The total mass of dark matter is what sets the critical density of the universe, deciding its overall shape. Observations show that our universe is flat, meaning there is just the right amount of dark matter and energy to keep the geometry of space perfectly straight. If there were just a bit more dark matter, the universe might have been closed, eventually collapsing back into a tiny point. But because the balance is so precise, we live in a universe that is open and vast, with plenty of room for galaxies to drift in the quiet dark. We have observed that dark matter doesn't seem to decay or change much over time. It is a remarkably stable and patient substance that has remained largely the same since the first seconds of the Big Bang, providing a steady foundation for the rest of history. The ratio of 5 parts dark matter to every 1 part of normal atoms is one of the great mysteries of science. If that ratio were different, the universe would look completely unrecognizable, perhaps having too many black holes or not enough stars to support life. In the first few minutes of the universe, dark matter influenced how much helium and lithium were created in a process called Big Bang nucleosynthesis. By providing extra gravity and pressure, it helped set the chemical recipe for every star that would ever be born. It is truly the most stable part of the cosmic recipe, a non-reactive and unchanging presence that doesn't explode or burn. While stars are violent and short-lived, dark matter is a calm and eternal background that simply exists, holding everything in its place. Some theories even suggest the existence of dark stars, giant, cool stars, that weren't powered by nuclear fusion like our Sun, but by dark matter particles annihilating in their cores. These would have been the very first objects to shine, glowing with a ghostly light in the young universe. These dark stars could have lived for a very long time, as long as they had a steady supply of dark matter to eat. They represent a beautiful alternative way for the universe to create light, using the energy of the unseen to illuminate the very beginning of time. In the quiet, invisible world of the very small, scientists explore the idea of FIMP, or feebly interacting massive particles. Unlike their more famous cousins, the WIMP, these particles are so incredibly shy that they never reached a state of thermal balance with the rest of the early universe, meaning they have drifted in a state of perfect, lonely isolation since the very beginning of time. There are also theoretical giants known as WIM Psilus, which are ultramassive particles that could have been created during the high-energy finale of cosmic inflation. These hypothetical heavyweights would be trillions of times more massive than a standard particle, representing a monstrous scale of dark matter that would exert an enormous gravitational pull despite being very few in number. Some researchers look toward the mirror matter theory, which imagines a hidden sector of particles that perfectly mirrors our own world of atoms and chemistry. In this version of reality, there could be dark atoms and dark chemistry that only share the force of gravity with us, existing like a ghost dimension that occupies the same space as our own without ever touching. To explain how these invisible particles might talk to each other, scientists have proposed dark photons, which would be the force carriers of a hidden electromagnetic field. Just as normal photons allow us to see light and feel magnets, these dark photons would allow dark matter particles to interact with one another in ways that remain completely invisible to our standard senses. In the realm of scalar field dark matter, the entire universe is thought to be filled with a massive, invisible field of particles called bosons. These particles are so light and numerous that they form what is known as a Bose-Einstein condensate, a strange state of matter where the entire field acts like a single giant quantum wave that flows through galaxies. When we look at the way light bends around distant objects, we are observing gravitational lensing, a phenomenon predicted by Einstein where mass curves the fabric of space itself. Because dark matter has mass, it acts like a giant, invisible magnifying glass in the sky, distorting the images of the galaxies that sit far behind it. Strong lensing is the most dramatic version of this, where a massive clump of dark matter can actually split the light of a single distant galaxy into multiple copies. This often results in a beautiful glowing circle known as an Einstein ring, which allows us to see exactly where the invisible mass is concentrated in the center of a cluster. A more subtle version is weak lensing, which doesn't create multiple images but slightly stretches the shapes of millions of galaxies. By carefully measuring these tiny smears across the entire sky, astronomers can build a statistical map of the clumpiness of the dark matter that fills the space between us and the stars. By measuring these distortions, scientists can effectively weigh the dark matter that is causing the bending, even though they can't see the matter itself. This technique is one of our most reliable scales for the universe, allowing us to calculate the mass of entire clusters of galaxies with incredible precision. Gravitational lensing is so powerful that it allows us to see the distribution of dark matter even in empty space, where there are no stars at all. It reveals that the darkness is not a void, but is filled with heavy, invisible structures that are just as real as the planets under our feet. The Bullet Cluster is perhaps the most famous piece of evidence for this, showing a massive collision between two groups of galaxies. In this cosmic car crash, the visible gas slowed down due to friction, but the dark matter sailed right through, proving that the invisible mass is a distinct substance that doesn't like to stick to anything else. Scientists also look for microlensing, which happens when a single dark object, like a tiny black hole, passes directly in front of a distant star. This causes the star to temporarily brighten in a very specific, predictable way as the object's gravity focuses the star's light toward Earth like a flashlight. This technique was used in surveys like Macho and Eros to search for dark objects in the Milky Way's outer edges. While they found some objects, they didn't find nearly enough to explain all the dark matter, which led scientists to believe that the invisible is made of particles rather than solid rocks. Observations of lensing have revealed that dark matter is not a perfectly smooth mist, but is actually quite clumpy. These clumps, or subhalos, are like invisible clouds of mass drifting within the larger galaxy, each one exerting its own small gravitational pull on the stars nearby. The light from Earendel, the most distant star ever discovered, was only visible to us because it was magnified by a factor of thousands by a cluster rich in dark matter. This natural telescope provided by the dark world allowed us to see a single star from the very beginning of time that would otherwise have been far too dim to detect. Cosmic shear is the technical term for the large-scale distortion of the entire universe's image caused by the cumulative pull of all dark matter. By analyzing this shear, scientists can determine a clumpiness parameter known as $S8, which helps us understand if the universe is becoming more or less structured over time. Lensing also helps us detect dark matter filaments, which act as the intergalactic highways of the cosmic web. These thin threads of mass are too faint to see with light, but their gravity is strong enough to bend the paths of photons traveling from the most distant corners of the cosmos. Some galaxies are so heavy with dark matter that they act as lenses for themselves, with their own invisible halos bending the light of their own internal stars. This creates a complex internal dance of light and gravity that helps astronomers measure the density of the galaxy's core. Time delay cosmography is a fascinating method where scientists look at multiple lensed images of the same object and notice that the light arrives at slightly different times. Because the light in each image took a slightly different path through the dark matter, these delays help us calculate the exact expansion rate of the universe. It is important to remember that dark matter does not slow down light. It only changes the geometric path that the light takes. Even the ancient light from the Big Bang itself has been subtly lensed and redirected by the dark matter it encountered on its 13 billion-year journey toward our eyes. Deep inside massive galaxy clusters, dark matter creates a potential well, so deep that it can trap gas and heat it to millions of degrees. This gas glows brightly in X-rays, and by mapping this glow, the Chandra X-ray Observatory can show us exactly how the dark matter is pulling the cluster together. In some theories, dark matter is thought to be collisionless, meaning that even when two massive clouds of it hit each other, the individual particles don't bounce. They simply pass through the gaps between each other, like two ghosts walking through a wall, maintaining their original speed and direction. This ghostly nature is why dark matter halos are often so much larger than the galaxies they contain. While normal gas can lose energy through collisions and sink to the center to form stars, dark matter keeps its energy and stays spread out in a wide protective sphere. Some physicists explore the idea of fuzzy dark matter, where the particles are so light that their quantum wave is larger than a solar system. This would mean that the dark matter in your room isn't a collection of points, but a single massive vibrating field that is perfectly smooth on small scales. This fuzzy nature would solve several puzzles in cosmology, as it would naturally prevent dark matter from clumping into tiny, dense spikes that would interfere with the orbits of stars. It represents a beautiful bridge between the world of quantum mechanics and the world of giant galaxies. We also use gravitational wave observatories like LIGO to listen for the background hum that dark matter might leave behind. If the universe is filled with a specific type of dark matter field, it might cause space itself to vibrate at a very low frequency that our sensitive lasers can detect. The Square Kilometre Array, a massive future radio telescope, will use the 21 cm hydrogen line to map how dark matter was distributed before the first stars even turned on. It will allow us to see the dark ages of the universe, a time when the only thing shaping reality was the invisible gravity of the web. New quantum sensors are currently being developed to detect the tiny kicks that a dark matter particle might give to a single atom. These sensors are so sensitive that they can measure movement smaller than the width of an atomic nucleus, hoping to finally feel the touch of the unseen. The Einstein telescope, a planned underground observatory, will look for the way dark matter affects the orbits of black holes. By watching how these giants spiral into each other, we can see if they are being dragged by a thick mist of dark matter, revealing the density of the void. Scientists can even detect kinks in the long streams of stars that circle our galaxy, which might be caused by a dark matter subhalo punching through the stream. It's like seeing a ripple in a ribbon of smoke, telling us that something invisible and heavy just passed through. The Dark Energy Survey has already mapped out a huge portion of the sky, identifying the footprints of dark matter by looking at how it pulls on millions of different galaxies. This massive map is helping us understand if dark matter is perfectly stable or if it is slowly changing over billions of years. In some models, dark matter might evaporate from the smallest galaxies if the particles are moving too fast to be held by the weak gravity. This would leave small dwarf galaxies with very little dark matter, explaining why some look lighter than our simulations predict. We are also searching for primordial black holes, which are tiny black holes that might have formed in the first second of the universe. If there are enough of them, they could act exactly like dark matter, drifting through space and providing the invisible gravity that holds galaxies together. If dark matter turns out to be a particle called an action, then the entire universe is essentially filled with a Bose-Einstein condensate. This would mean the cosmos is one giant, interconnected quantum fluid, a silent and perfectly synchronized sea of energy. The radial acceleration relation remains a deep mystery, showing a perfect link between how much visible matter there is and how fast the stars are moving. It suggests that even though we can't see dark matter, it is perfectly in tune with the atoms we can see, as if they are dancing to the same hidden rhythm. By observing how these subhalos interact with the Milky Way, we can learn about the temperature of dark matter. If the clumps are sharp and dense, the dark matter is cold. If they are blurry and spread out, the dark matter might be warm, giving us a clue to its true identity. As we move through the galaxy, the dark matter wind changes direction depending on where the Earth is in its orbit around the Sun. This constant, gentle flow is a reminder that we are always moving through a vast, invisible sea that connects us to the furthest reaches of space. Dark matter is truly the missing piece of the cosmic puzzle, the substance that makes all our math work and all our observations make sense. Without it, the universe would be a fragmented and confusing place, but with it, everything falls into a beautiful, predictable order. It is the reason we are here today, as its gravity provided the safe harbors where the first galaxies could grow and stars could eventually create the elements for life. We are, in a very real sense, the children of the dark matter that built the world. The study of this invisible world is a journey into the very heart of reality, a quest to understand the 95% of the universe that remains hidden. Every new experiment and every new telescope brings us one step closer to finally meeting our silent partner face to face. Dark matter provides the essential cosmic gravity well in which our own Milky Way galaxy safely rests. Imagine a heavy ball placed on the soft trampoline, creating a deep dip that pulls everything else toward it. Dark matter creates this same kind of protective pocket in space, allowing our stars to gather and stay together in a stable home. It is a remarkably stable and non-reactive presence, existing as a silent foundation that never changes. Unlike the volatile gases and burning stars that can explode or collide, dark matter simply exists without any drama, providing a calm and reliable background that supports the rest of the universe. This invisible substance doesn't create fire or explosions, nor does it produce the blinding light or intense heat of a sun. Instead, it offers only a gentle, persistent pull, acting like a soft hand that guides the movements of the cosmos without ever causing the violent friction that normal matter often does. The dark matter in our own galaxy is moving in a vast, slow halo rotation that surrounds the bright spiral where we live. While we can see the stars of the Milky Way spinning, they are actually being carried along by this much larger invisible cloud that rotates with a rhythmic, ancient pace. The total mass of dark matter within the Milky Way is truly staggering, estimated to be roughly 1.5 trillion times the mass of our own Sun. It is a weight so immense that it is difficult to imagine, yet it is this very mass that provides the heavy anchor needed to keep our entire galactic neighborhood in place. Most of this incredible mass is located far outside the bright spiral arms where we live, extending into the suburbs of our galaxy. This means that while we look at the beautiful center of the Milky Way, the true power and weight of our home actually lie in the vast dark reaches that surround us. Dark matter is the ultimate expression of what scientists call the unseen universe, reminding us that most of reality is hidden from our eyes. It is a humbling thought to realize that for every bit of light we see, there is much more hidden in the shadows, working quietly to maintain the balance of everything. It is more like a ghostly fluid than a collection of hard, solid rocks or cold dust. Because it can pass through things without hitting them, it flows through space and through us like a silent stream, filling the gaps of the universe with a liquid-like consistency that never ripples or splashes. The presence of this invisible fluid is felt even in the steady and predictable orbits of the planets in our solar system. While we usually think of the Sun's gravity as the only force at play, the background pull of the galaxy's dark matter helps define the very path our Earth takes through the stars. Dark matter is the essential foundation of the standard model of cosmology, which is the master blueprint scientists use to explain how the universe works. Without this invisible ingredient, our mathematical equations for the universe would fall apart, leaving us unable to explain how we got here. It is the primary reason why the early universe didn't remain a uniform, boring cloud of gas forever. By clumping together early on, dark matter created the seeds that pulled the gas into tight enough pockets to ignite the first stars, bringing the first light to a once dark world. On the largest scales of reality, dark matter clusters are the absolute largest objects in the entire universe. These aren't just single points of light, but massive, sprawling structures of invisible weight that define the layout of the cosmic map on a scale that defies human comprehension. These invisible giants can be hundreds of millions of light years across, stretching further than the distance between many thousands of galaxies. They are the true titans of the cosmos, providing the framework upon which the entire history of the universe is written. One of the most impressive of these structures is the El Gordo cluster, which is one of the most dark matter-heavy structures ever discovered. Its name means the Fat One in Spanish, reflecting its status as a heavyweight champion of the universe, held together by an incredible concentration of invisible mass. Dark matter is essentially sterile in a biological sense, meaning it doesn't form complex structures like DNA, proteins, or life. While normal matter can become complicated and alive, dark matter stays simple and pure, never changing its form or entering into the messy chemistry of living things. It is the most simple form of matter in existence, interacting with the rest of the world in only one or two very basic ways. It doesn't care about electricity, magnetism, or chemistry. It only cares about gravity, making it a clean and uncomplicated part of the natural world. Dark matter serves as the silent background against which the beautiful drama of life and the birth of stars unfolds. It is like the stage in a theatre. While we watch the actors and the lights, the stage itself remains still and unmoving, providing the necessary support for the show to go on. Every brilliant star you see in the night sky is like a single candle placed on a massive, invisible mountain. The star provides the light, but the mountain of dark matter provides the height and the solid ground that allows that light to be seen from so far away. Without that invisible mountain, the light of the stars would have nowhere to sit and no way to stay organized. The galaxies would simply be loose collections of wandering suns, drifting aimlessly through the void without a home or a structure to keep them together. Dark matter is as much a part of nature as the trees in a forest or the wind that brushes against your skin. Even though we cannot see it or touch it, it is a natural and necessary part of our environment, existing everywhere in the space between us and the furthest galaxies. It acts as a permanent bridge between the very beginning of time and the present day in which we live. The dark matter that first clumped together billions of years ago is the same dark matter that is holding our galaxy together tonight, a constant thread running through all of history. The search to understand dark matter is a truly global effort, bringing together scientists from every continent and every culture. It is a beautiful example of how the mysteries of the stars can unite people in a shared journey of curiosity and discovery. It remains one of the few great mysteries of science that we are actually very close to solving. Every year, our tools get better and our understanding grows deeper, bringing us to the edge of a discovery that will change how we view our place in the cosmos. Every new map we make of the distant universe confirms that dark matter is exactly where we expect it to be. Its presence is no longer a guess, but a verified fact that shows up every time we look at the way light bends and galaxies move in the deep sky. It is the cosmic anchor for the stars, providing the stability they need to shine for billions of years. Just as an anchor keeps a ship from drifting in a stormy sea, dark matter keeps the galaxies from being lost in the vast, expanding ocean of space. Dark matter is the underlying reason why the night sky looks the way it does to our eyes. The specific patterns of the constellations and the glow of the Milky Way are all dictated by the invisible hand of gravity that arranged them into their current positions long ago. It ensures that galaxies have enough weight and substance to keep their beautiful shapes over long periods of time. Without this extra mass, the elegant spirals and glowing ellipses of the galaxies would have flattened out or dissolved into the darkness eons ago. On the very largest scales, the density of dark matter is remarkably uniform and consistent throughout the universe. This tells us that the laws of physics are the same everywhere, and that the invisible foundation of the cosmos is steady and reliable, no matter where you go. It is the most peaceful substance in existence, as it never clashes, burns, or enters into conflict with other matter. It simply drifts and pulls, existing in a state of perfect harmony with the rest of reality, never seeking to change anything but the path of gravity. Scientists are currently building the most sensitive tools in the history of the world to try and hear the tiny, silent whisper of a dark matter particle. These experiments are the ultimate testament to human curiosity, as we build giant machines just to catch a glimpse of the invisible. The dark matter wind is a real phenomenon that changes direction as the Earth moves in its orbit around the Sun. It is a gentle cosmic breeze that we are sailing through right now, a reminder that we are constantly moving through a vast sea of unseen energy. This wind is a constant, gentle flow that passes through our solar system, our houses, and our bodies, without us ever knowing. It is a quiet companion to our journey through space, a silent stream that has been flowing since the dawn of time. Dark matter is the missing piece of the cosmic puzzle that makes everything else fit together. When we include it in our calculations, the universe makes sense. The stars move correctly, the galaxies form at the right time, and the history of space becomes a clear and beautiful story. It is the reason we are here tonight, as its gravity allowed the first galaxies to form safe harbors where stars could create the elements needed for life. We owe our existence to this invisible partner, the silent architect that built the house in which we live. It is a gentle reminder that there is always more to learn and more to discover about the world around us. Just because we can't see something doesn't mean it isn't there, and the mystery of the dark is an invitation to keep looking up with wonder. Dark matter is the ultimate unknown, yet it is also the most everywhere thing in the universe. It fills the voids, surrounds the stars, and permeates the space between us. A reminder that we are never truly alone in the vastness of the cosmos. It is the invisible force that guides the stars through the long night, keeping them on their steady and predictable paths. Like a lighthouse that we cannot see, its gravity shows the way, ensuring that the universe remains an organized and beautiful place. It is a quiet, constant presence in an ever-changing and often violent universe. While stars explode and galaxies collide, the dark matter remains a calm and steady influence, providing the peace and stability that the universe needs to thrive. The study of dark matter is truly a journey into the heart of reality itself, a quest to find the source of the gravity that holds us all. It is a path that leads us from the smallest particles to the largest structures, revealing the deep connections that bind the universe together. In the end, dark matter is the silent, gravitational embrace that holds the entire universe together in one big, beautiful family. It is the invisible hug of the cosmos, a quiet and eternal force that ensures nothing is ever truly lost in the dark.